Greetings everyone, Professor Simon here, ready to dish out some more Calc 2. You ready? Next advanced integration technique, one of my favorites, trigonometric substitution. This is a more inverted substitution method than the traditional U sub that you would have learned in Calculus 1. In Calculus 1 with the U sub, you would have seen that typically we pick some variable to represent a chunk of something in an integral in an attempt to reduce the complexity of the structure. With trig substitution, we more along the lines of do a substitution of pieces in the integral to sort of parallel the complexity in a structure with trigonometry rather than radicals and binomials with squares and things of this nature. So there are certain things that we specifically use trigonometric substitution for. That doesn't mean that trig subs is the only way that these problems can be solved, and I will show you when that comes up that you actually do have choices. All of these advanced integration techniques have multi-uses like that, and some integrals have multiple paths, and some of them are more work than others. But trig subs, it's not about a reduction in complexity as much as normal subs is. Okay? Trig subs is all about paralleling it into the trigonometric structure and then using our knowledge of trigonometry to more easily navigate the structure that it's been converted into. Much like the integrals that we would have just discussed in the last lecture, those kind of trigonometric integrals can sometimes be easier to just get through the different intricacies because of all the different identities and such and things like that. A good many of these integrals can be done without trig substitution, but it requires a lot of algebraic finesse and probably a lot more brain and time crunching to make the structure look like it needs to so that you can see what to do. Trig substitution simplifies the process of showing you a pathway to quickly get to the solution of the integral. So enough chat, let's take a look. There's three main setups for trig substitution, and you don't need to memorize them, okay? Whenever I do one of these trig subs, what I do is I set up a right triangle that carries all of the information of the substitution inside of it. So it's sort of like a Rosetta Stone, a key of transferring information from one type of the integral to the trig type, okay? So what I do is I look at the binomial with the squares in it, okay? That's what you have. You have three different types. You have the sum of squares, you have the difference of squares where the variable is in the tail of the subtraction, and you have the difference of squares where the variable is the lead in the subtraction. See, that's actually two different ways of looking at the subtraction of the squares there, and it's important in your substitution to note which one you have. Okay, so the first one, the sum of squares, it doesn't really matter where your variable is there, so if it's the front or the back of the binomial. And typically it can be really to any power, the binomial itself. We see a lot of those binomials to first, second, third powers, and then we do see a lot of those binomials to radicals, half powers, 3/2 powers, things like that. Very common to see a square root with these things, and trigonometry helps us resolve those a lot more easily. Okay, so what happens is you locate your binomial, you decide which of the three you have, and depending on which of those three, you set up your triangle with the variable x or y or whatever it is, and then whatever the number from a squared is, the a part. So in other words, if it were 16, the a would be 4, right? If it were 20, you would say square root of 20 or 2 square root of 5. For your a value, okay? So then what you do is, for example, when you have the addition, the sum of the squares, I use those two as the legs so that when I use the Pythagorean theorem on these two legs, they sum the squares. So in my triangle, I should see the structure that I'm trying to replace in the integral. That's important that that structure appears, and that's why knowing which one of the three binomials you have changes your choice. Okay? So for example, if I have the difference of squares where the variable is in the tail of the subtraction here, where it's the second term, I always use the front of the subtraction as my hypotenuse. So A would be the hypotenuse. And then I choose x to be opposite theta here so that I can get sine. Okay? Whereas over here, x is also opposite theta, but notice I'm getting x is equal to tangent there. Because whenever you set these up, you want to use the x and the a in conjunction to create the substitution. So here, notice x is the opposite and a is the adjacent because that's how I got my sum of squares. Okay? Whereas here, x is the opposite and a is the hypotenuse, so that I'll get a squared minus x squared in the other leg. Right? And the same thing goes over here. If I have the difference of squares where the variable is the lead of the subtraction, of course, the lead of the subtraction should always be the hypotenuse. So if I let a be one of the legs, then I get the x squared minus a squared in the structure that I need to repeat like that. Okay? So here, I'm getting that x over a is the tangent of this angle theta that I've drawn. And that becomes your substitution. And that's what I was getting back to, saying this is more like an inverted substitution, because instead of the substitution being a replacement of a whole structure immediately, the actual substitution is letting x be equal to some sort of trigonometric setup. Okay? And you'll notice what I actually did was I solved for x, because x over a is tangent of theta. But then I just multiply the a so that I have x equals a times tangent theta. Then immediately, as required with any substitution, you need a differential portion, right? So from x, I take the derivative to get dx. And of course, the derivative of tangent is secant squared. So I have a secant squared d theta. Also, more information inside of the triangle that you would need to have is to note that the hypotenuse divided by the adjacent is the secant of this theta. And so if I multiply the a over, I have that the square root of x squared plus a squared is equal to the a times secant theta. And that's important because that chunk right there, the x squared plus a squared, is part of your integral. That's what made you choose the setup. So that particular binomial is going to be somewhere in your integral. You're going to want to replace your x's. You're going to want to replace your dx. That's what makes the integral change possible. But then also you're going to want to bring in this other structure and replace those parts as well. Okay? Now, some people might just say, oh, just remember this and then plug that tangent into something with the secant and you can create it using Pythagorean identities. Yes, great. That takes time though. Okay? If you set up the triangle and you have all of this information right there at your disposal, then you can immediately pick out, oh, this over this is secant, or this over this is sine, and you can solve for things immediately that you need for your integral. Okay? So here's an example integral that would use this particular setup. And you probably notice that you can actually already do this integral without using trig subs, and that's mainly because you know of the antiderivative of the 1 over x squared plus a squared. So this one's, pretty straightforward. But if you didn't know that antiderivative, then there wouldn't be any other way for you to cross over from something rational into something trigonometric like an inverse tangent. And you'll notice this is going to be an inverse tangent solution to this integral. And notice it does actually involve a tangent substitution because of the way that thing is set up. Okay? So in a minute I'll work all the examples, but so you can see this would be a prime example of using this particular structure. Here's an example of using this sine substitution. Okay, Anytime I have a number minus the x squared right here, so the 9 tells me that my a is 3 in this one, right? So I have 3 squared minus x squared, and it fits this setup. Incidentally, you could have set x to be either the adjacent or the opposite, and it would still work out fine as long as the a is the hypotenuse, because it's the front of the subtraction. I always choose my x in a certain spot, or my a's in a certain spot, so that I get the trig functions that do not have co with them. Okay, you'll notice I have tangent, I have sine, I have secant as the substitutions that I prefer to use. And that's mainly because the derivatives and integrals that involve those typically leave out as many negatives as possible. If I did swap the x right here, it would still work perfectly fine, but I would have more negatives to worry about because the derivative of cosine gives me a negative with the sine. Okay, now of course negatives are inevitable, but the way that I have us choosing these minimizes the number of negatives that you'd have to keep track of, and that's just a nitpicky part for me. Okay, but as you can see, whatever's the front of a subtraction in these differences of squares is what I pick for my hypotenuse, and then from there I pick the appropriate side to give me one of the trig functions, one of the main ones, not one of the co-functions. Okay, so here if a has to be the hypotenuse, then I pick x to be opposite, because opposite and hypotenuse give me sine. Whereas here x has to be the hypotenuse because it's the front of the subtraction, and I pick a to be adjacent because hypotenuse over adjacent gives me secant. And then everything evolves the same way for all of these situations. Once you set up your triangle, you find your substitution for x, you do your differential dx so that you can do that replacement, and then you always set up whatever the radical portion, the other leg or the other side that you use the Pythagorean theorem to solve out, right? The binomial portion. You want to have something solved for that piece too. Those 3 pieces of information will make the substitution roll very quickly. Okay, you'll notice I have the same 3 pieces of information. You will still need all of this information at the end of the integral as well, because you're going to have to come back out of the trigonometry back into whatever, x or y or whatever you were in originally. Okay, and having these structures laid out also makes that go quickly. Okay, so these are the 3 main structures, and in the next scene I'm going to work these 3 examples, and then I'll work a few more after that as well. Okay, so to go ahead and put the nail in that particular coffin we were just talking about, let's work out these 3 examples to get some beginning here. Okay, so the simple one, the one you already know the solution to, right? It's going to use the inverse tangent. But let's use trig substitution to actually work this one out without any prior knowledge of inverse trig. Inverse trig antiderivatives is what I mean. Okay, so I approach the integral and I notice the binomial x squared plus 4. That right there sets off a big red flag. Hey, let's try trig substitution, because I see the square sum of squares there. So immediately I realize, oh, well, since those 2 are added, then I'm going to set up a triangle, a right triangle with an angle, theta. And I know that I'm going to let x and 2 be the 2 legs. Specifically, x being the opposite because I want to have tangent, not cotangent. Okay? It would still work with cotangent, but I'm minimizing my negatives. From here, I notice that if I do x squared plus 2 squared and square root, I'll get the length of the other side. So that's square root of x squared plus 4 would then be the length of the other side via Pythagorean theorem of the x and the 2. Okay, so the x and the 2 come from the integral, and then I use Pythagorean theorem to finish out the third side there. So then my substitution comes in right here by noticing that x divided by 2 is the tangent of theta. Therefore, x would be equal to 2 tangent theta. And then I take the derivative to get my differential, dx. Derivative of tangent is secant squared, and then d theta. And lastly, I notice that hypotenuse divided by adjacent would be secant. Therefore, the square root of x squared plus 4 divided by 2 would be secant of theta. Or in other words, the square root of x squared plus 4 would be equal to 2 secant theta. So there's my 3 pieces of data that I need to read from the beginning triangle there. And now I'm going to use those 3 to substitute. Okay? So first thing I notice is that, of course, I can replace my dx with the 2 secant squared d theta. Okay, so my integral, I have 1, and then I'm going to have times 2 secant squared theta d theta. That's from the dx. Next, I have x squared plus 4 all to the 1 power, right? This is all to the 1 power. That would be the same thing as this guy right here squared, right? Because this is a square root of x squared plus 4, okay? So the actual x squared plus 4 from this statement right here would have to be the 2 secant theta all squared from that statement right there. So that's what I'm going to replace. I'm going to say right here that x squared plus 4 is equal to 2 secant theta, and then that whole thing squared. So hopefully you see where this is going. I have a secant squared in a denominator. I have a secant squared in a numerator, right? And then this 2 squared here is going to be a 4, and I have 2 over that 4. So this integral has then become 1/2 the integral of d theta. This particular integral falls apart. And it's because it's one of those straightforward anti-derivative integrals, right? So in this case right here, the 1/2 integral d theta simply gives me 1/2 theta plus c as the solution to this integral. And then we just need to ask ourselves, well, wait a minute, what was theta equal to? Well, the simplest was directly from this substitution here, right? Right here, I can see that x over 2 is equal to tangent theta, right? We already knew that. So to solve for theta, I simply need to do the inverse tangent there. So then to finish this up, I have this is equal to 1/2 inverse tangent of x over 2, right? Because I'm doing inverse tangent right here of the x over 2 plus c. And there's my solution to that integral, which is what we already expected, right? Because that's how we set up the antiderivative of 1 over x squared plus a squared. But this is how you can show that it really works the algebraic calculus way. Okay, let's go again. For this integral right here, the first thing I notice is the 9 minus x squared, being a difference of 2 squares binomial. That sends up a big red flag. Hey, let's do trig substitution, right? Okay, so trig subs here. I'm going to draw my triangle, right? It doesn't matter which direction you draw your triangle. It just matters to help keep you on the path here. Pun intended. So I've got my triangle, and since the 9 is in the front of the subtraction, that means I'm going to put a 3 for my hypotenuse. And then so that I can have something like a trig function that doesn't have a co, I'm going to put the x as the opposite because opposite over hypotenuse, right? That's going to give me sine. And then I notice that I'll get 3 squared minus x squared in a square root for the adjacent side there using Pythagorean theorem. So then my information from the triangle starts with this. X over 3, right? X over 3 is equal to sine theta, right? Then this tells me that x is equal to 3 sine theta. So I take the derivative. Dx is then 3 cosine theta d theta. And lastly, I notice that adjacent over hypotenuse, the square root of 9 minus x squared over 3 is equal to cosine theta. So I can get that third piece of info of my square root of 9 minus x squared is equal to 3 cosine theta. So I've got my 3 important pieces there. And I'm going to do my substitution now. Okay, so equals integral. I've got a 1 on top. X squared is going to be 3 sine theta squared. Like so. Then the square root of 9 minus x squared, I see that that's directly replaced with 3 cosine theta. So times 3 cosine theta. And then dx is 3 cosine theta d theta. So times 3 cosine theta d theta. Immediately I notice that the 3 cosine thetas here are going to reduce, right? So these are gone. And that leaves me with a 9 because of the 3 squared in the denominator. So I'm going to pull that out. 1/9. And then I have a 1 over sine squared. Well, 1 over sine is cosecant. And 1 over sine squared is cosecant squared. And then I still have a d theta. Also a very quick antiderivative. Antiderivative of cosecant squared is negative cotangent. Plus c here. Right? Negative cotangent theta is the antiderivative of cosecant squared. Okay, now I'm in that last phase where I need to come back up here and say, all right, what is cotangent theta actually equal to? Because I need to replace that back for information in X world. Well, cotangent is adjacent over opposite, right? So cotangent is going to be the square root of 9 minus x squared, that's adjacent, over the opposite x. So in other words, when I convert this back out, I have negative 1 over 9 times the square root of 9 minus x squared over x plus c. Or in other words, if you want to write it succinctly, you could just say negative square root of 9 minus x squared all over 9x plus c. Either one of those two last lines works just fine. Okay? And then this third example over here. I hope that you'll notice right away that I don't actually need trig subs for this one. I can actually do this one with an ordinary U substitution from Calc 1. We'll work that one out in a minute. Let's continue with the flow of trig subs, and then I'll show you the other way too. Okay, so I'm going to start by noticing that I've got my difference of squares there, my binomial. So that tells me trig subs is viable. I'm going to set up my triangle. And I notice that x is in the front of the subtraction. So I put x as my hypotenuse. And then 1 squared is 1. So I'll put 1 as the adjacent. And remember, the reason I'm picking the adjacent is because I want to do hypotenuse with adjacent, which would give me secant. If I picked 1 as the opposite over here, hypotenuse over opposite would be cosecant, and that would just give me more negatives, which is fine, but if I can avoid them, I should. All right, so with this particular setup, x squared minus 1 squared in a square root gives me square root of x squared minus 1 for the other leg of the triangle. Okay, so then I notice x over 1 is the secant here. In other words, x is equal to secant theta. And then my differential, dx, is going to be secant theta, tangent theta, d theta. And then my last piece over here, the square root of x squared minus 1 over 1, right, that's opposite over adjacent, is going to be the tangent of theta. Or in other words, the square root of x squared minus 1 is equal to tangent theta. So I've got my substitution ready to go here. So then this integral equals x cubed. That's going to give me secant cubed. Square root of x squared minus 1 is equal to tangent, so times tangent theta. And then dx is a secant theta, tangent theta, d theta. So I'm going to mash all of that together. And I've got an integral of secant to the 4th times tangent squared. D theta. So if you remember from the previous section, we need to play around with this a little bit and possibly do another substitution, just a normal u subs, in order to make the trig work. So that's what I'm going to do now. I'm going to convert this like this. I have an integral of 1 plus tangent squared, and that's one of the secant squareds coming to 1 plus tangent squared, times tangent squared times secant squared theta d theta. Okay, so real quick, throw back from last section, I saved a secant squared off to the side because I know the derivative of the tangent is the secant squared, so I can do my u substitution. I converted the rest of the secants that I wasn't saving into 1 plus tangent squares. So everything is in terms of tangent and then the derivative of tangent. So at this moment right here, if I let u equal tangent theta, then du is secant squared theta d theta. So then my integral becomes 1 plus u squared times u squared du, which I can quickly turn into the integral of u squared plus u to the 4th du, which the antiderivative would then be 1/3 u cubed plus 1/5 u to the 5th plus c. All right, now we need to get all the way back up to x. We actually went through 2 substitutions. We went through the trig substitution, and then I did a normal u subs. Fortunately, we have a really direct connection here. Notice u equals tangent theta, right? And tangent theta has already been equal to something as well. So basically, we just said that u is equal to the square root of x squared minus 1, right? Transitive property, if you will. One thing is equal to something, another thing is equal to that same thing, so u has to be equal to the square root of x squared minus 1. Okay, so then if u, right here, u is equal to x squared minus 1 to the 1/2. That's what this is telling me right here. But then I need to raise it to the third power. So then this is 1/3 times x squared minus 1 to the 3/2, because it's the third power with the half power, plus 1/5 x squared minus 1 to the 5/2 power, plus c. Okay? Now, incidentally, you could have done this one in Calc 1. And this is kind of what I was getting at earlier when I was talking about trig subs always having other options. Well, not always, but sometimes having other options. If I were to work this integral, x cubed square root x squared minus 1 dx, if I split it up like this, make it equal to 1/2 integral x squared square root of x squared minus 1 2x dx. Okay, so notice what I did was, instead of x cubed, I split the x squared and an x right here, and then I did a 1/2 and a 2. And the reason for that is, if I let a substitution like w equal x squared minus 1, then dw is 2x dx, right? So the 2x dx here that I have is going to be my dw, and then the square root of x squared minus 1 will become the square root of w. And also, since w is equal to x squared minus 1, then that means that w plus 1 is also equal to x squared. So if I substitute all three of these pieces into this integral, what I get is 1/2 times the integral of w plus 1 times w to the 1/2 dw, which, if I distribute the w to the 1/2, you'll notice that I have w to the 3/2, and then I have to integrate that. So, well, I'll go ahead and write it out. 1/2 integral w to the 3/2 plus w to the 1/2 dw. And then that's 1/2 times 2/5 w to the 5/2 plus 2/3 w to the 3/2 plus c. And you'll notice right away that the 1/2 wipes out both of the 2's in these numerators after doing those. And w is equal to x squared minus 1. So if I plug those back in, you'll notice I exactly get that same answer. And sure, it seems like less steps, but it is still an involved substitution. Okay? So it ends up being about the same amount of work mentally. This one does have a little bit more writing, just because I wanted to make sure and follow all the steps. But as a whole, trig substitution makes these complicated integrals simpler, even if the actual structure itself is not simpler. I mean, having trig in an integral is not necessarily simple, but we have really nice connections and identities for trigonometry that sometimes makes the flow much easier on these, just to see the pathway. Okay, but there is always a possibility. There's always a possibility that there's more than one way to do it. Okay. Now let's get a couple of examples using definite integrals. Here's a very popular one that goes along with trig subs. Show that the area of a circle is pi times the radius squared. Okay, so remember, we can use definite integrals to represent areas between an axis and the curve of a function. So what I'm going to do is I'm going to integrate a corner, 1/4 of a circle. Okay, so the corner right here of the circle is going to be 1/4 of the area, and I'm going to use just a generic r for the radius here. So x squared plus y squared is going to equal r squared, and therefore y would be equal to the square root of r squared minus x squared. So then what I'm actually going to be doing here is I'm going to be getting my area is equal to 4 times the integral from 0 to r of the square root of r squared minus x squared dx. So I'm just integrating that function, right, from 0 to r, and that's 1/4 of an entire circle, so I just do times 4 to accommodate that particular feature. Okay, so then next, I notice that this is a trig substitution because of the difference of squares binomial there. So then I begin drawing my triangle out. I draw my triangle to do my substitution. Here's my theta. Here's my right angle. R is in the front of the subtraction, so R is the hypotenuse. And then x would have to be the opposite to make it work the best. And therefore the square root of r squared minus x squared is here. Now I do want you to notice something, that I could also have drawn this particular substitution actually inside of my shape, right, like this. Okay, and the angle in there would be completely representative of the same way. I'm just going to stick with the generic one though, the way we have been doing it. My substitution therefore is that x is going to equal r times sine theta, right, because x over r is going to be sine theta. Therefore dx is going to be r cosine theta d theta. And lastly, this square root here of r squared minus x squared over r is cosine. So it's going to be equal to r times the cosine of theta. Right? That's just your basic adjacent over hypotenuse there. I just multiplied the r over. I'm going to use this to substitute into this integral here. So then I have that my area is equal to 4 times the integral. This radical right here is r times cosine theta, and then dx is also r cosine theta d theta. And then the limits of my integration I can change. When x is equal to 0, okay, when x is equal to 0, then sine theta times r equals 0. So in other words, sine theta equals 0, or in other words, theta is 0. So 0. And that makes sense, right? Because we're going to do theta equals 0. And then you should expect, since this is a corner of it, right, you should expect that this is going to go up to a 90-degree angle. Let's double check that here. When x is equal to r, then I have that sine theta is going to be equal to 1. Because I'll have r divided by r. In which case that means theta is pi over 2, 90 degrees, pi over 2 radians. So I would put pi over 2 here. Okay, let's simplify this a little bit. I have that this is now equal to 4 times r squared, because those are constants, I can pull them out. Integral from 0 to pi over 2 cosine squared theta d theta. And I just need to be able to do the integral of the cosine squared. Well, remember, to do the ones that are strictly even powers with sine and cosine, I need to do the power reduction formulas. So my area is equal to the 4r squared integral from 0 to pi over 2. Cosine squared is equal to 1/2 1 plus cosine 2 theta d theta. And then I just need to do this integral. The 1/2 times the 4 gives me 2 r squared. And then the antiderivative of the 1 is theta. And the antiderivative of the cosine 2 theta is going to be a 1/2 sine 2 theta. And then that's evaluated from 0 to pi over 2. Okay, so the first thing I want you to notice is that when I plug in the 0 for both of these things, I get 0. Because obviously theta equals 0 will give me 0. And sine of 0 will also give me 0. So the 0 is not actually adding anything here. They're both zeroed out. Next, when I plug pi over 2 in here, notice I'll have 2 times pi over 2, which is pi, which will give me sine of pi, which is also 0, right? So this particular piece completely zeroed out. All that's left is to plug pi over 2 into the theta. Okay, so then I have that my area is equal to 2r squared times pi over 2. And then, of course, plus the 0 from that, and then minus the zeros from the other two pieces, right, which is the things that I was crossing out earlier. But then notice that exactly gives me pi times r squared for my area. Okay? All using trig substitution. Here's an interesting integral for us. It actually has a 3/2 power in it this time. But again, the first thing I notice is the difference of the squares there, right? Something that requires me to set up a trig subs. So let's do it. I see the 16 minus x squared, so I draw my triangle, right, like so. And then I know that my 4 has to be a hypotenuse because it's the front of the subtraction. I'm going to let x be the opposite so that I can let x equal 4 sine theta be my substitution. That, of course, means that the bottom here is going to be the square root of 16 minus x squared. And I can finish out my substitution. dx is going to be 4 cosine theta d theta. And the square root of 16 minus x squared is going to be equal to 4 cosine theta as well. Alrighty. So now for my integration here, this is going to be equal to the integral x squared, right? I'm going to have 4 squared sine squared theta. Okay, now in the bottom, pay attention here. This is a 3/2 power, right? Technically, this piece right here is a 1/2 exponent. So 16 minus x squared to the 1/2 is equal to 4 cosine theta. So what I would actually be doing to make this the 3/2 power is I would have to take the third power on both sides here. That would make this the 3/2 power of that. So this chunk right here is 4 to the third times cosine to the third. And then there's the dx, which is 4 cosine theta d theta, right? Okay, so notice I've got 4 squared times 4, which is 4 cubed, and I've got a 4 cubed in the denominator, so the 4's are going to all wipe out. I also have a cosine wiping out with one of my cosine cubed constituents too. So I'm left with an integral of sine squared theta over cosine squared theta d theta, which I will treat as a tangent squared theta d theta And the reason for that is I knew that I could convert tangent squared pretty easily into something that I could do the antiderivative of. So tangent squared is secant squared theta minus 1, which I know both of the antiderivatives of those, right? Antiderivative of secant squared theta is tangent theta. And of course, the antiderivative of 1 is just theta itself. Now, I've kind of let it slide a little bit for a few moments, but we didn't convert our limits. So that's why I'm not putting the plus c here. I'm going to go back up now, and let's figure out what those limits are. When x is the square root of 12, right, then I've got square root of 12 over 4 is equal to sine theta. Well, if you simplify that a little bit, I'm hoping that you'll recognize it. You get the square root of 12 is 2 square root of 3 over 4, which gives me square root of 3 over 2 is equal to sine theta, like so. Okay, so then I'm going to pick the quadrant 1 answer for this, right? Square root of 3 over 2 with a sine value is 60 degrees, or in other words, theta is pi over 3. Okay, so then that's going to be my upper limit, pi over 3. Pi over 3, pi over 3, pi over 3, and pi over 3. Okay, what about the other end on that one? When it's 0. When x is 0, that one's pretty straightforward. That means I have 0 is equal to sine theta, which of course is going to happen to us when theta is equal to 0. So my lower limit here is still 0. All right, so let's plug this stuff in. The tangent of pi over 3, or 60 degrees, is square root of 3 minus pi over 3. Tangent of 0 is 0, and then theta being 0 is 0. So here's my exact answer. Square root of 3 minus pi over 3. Here's an example with a beginning use substitution that leads into a trigonometric substitution. So I have the integral e to the x times the square root of e to the 2x minus 4 dx. And I'm noticing the binomial pattern here where I have something squared and 4 is also 2 squared. And I see the squared. Normally we don't think of exponentials that way. But the exponential out here is not the same power as this one. So we tend to think of this one as the square of that one. That would be an easier way to sort of think about it, because I won't be able to do just a normal u sub for this whole chunk, since this is not the same exponent as that one. However, what I can do is I can let my u equal to e to the x, which would mean du would be e to the x dx, which I happen to already have. This then simplifies the integral into the integral of the square root of u squared minus 4 du, which is ready for a trig substitution at this point. So then I come back and I look, oh look, there's my binomial. I can then set up my triangle, right? The same way we've been doing it. I have my angle theta. Since u is in the front of the subtraction, I put u on the hypotenuse. I would then also put the 2 as the adjacent so that I can get my secant. And then the square root of the u squared minus 4 would then be the other leg of the right triangle. Okay, so then my substitution, as we stated just a moment ago, u is going to be equal to 2 times secant theta, which would then mean du, ironically, right? It's kind of like we're reversing the substitution here. It's almost like this wasn't even needed. But, you know, it's nice to see the structure. du is then 2 secant theta times tangent theta d theta. And then, of course, I can set up my square root of u squared minus 4 would be equal to 2 tangent theta, right? From the opposite over adjacent there. Okay, so then my integral continues. The square root is equal to 2 times tangent theta, so I have 2 tangent theta just from this piece here. Then du is another 2 times secant theta tangent theta d theta, which brings my integral totally up to 4 integral of tangent squared times secant theta d theta. And this goes back to that last section again where we need to handle the trigonometric integrals. So I'm going to have to find a way to get this all in one trig function. And I can't really save anything as a derivative of anything else here. Secant squared would work for tangent, but I don't have that. Secant times tangent would work for secant, but then I'd have a tangent left over. That's not going to work very well either. So my only recourse then is to convert this tangent squared here into a secant squared minus 1. And then I'm going to distribute that secant into that parentheses, which is going to result in this integral. I'll have 4 times the integral of secant cubed theta minus secant theta d theta. Okay, and then naturally what I'm going to be doing is taking the antiderivative of the secant cubed and the secant separately, and those are both things that we've seen before. The antiderivative of secant theta, or I talked about in the Calc 1 lectures, and the antiderivative of secant cubed, we performed that one in the last 2 lectures ago in integration by parts. So both of those have solid antiderivatives that we've discussed. Let's do that. I then have 4 times the antiderivative of the secant cubed is 1/2 secant theta tangent theta plus 1/2 ln absolute value of secant theta plus tangent theta. Then minus the antiderivative of secant theta, so then that's minus the ln absolute value of secant theta plus tangent theta, absolute value, like so, plus c, right? And 4 is multiplied throughout the entire piece. So then I'm going to distribute the 4 to everything, and I'm noticing that these 2 chunks are like terms, so I'll combine that as well. This is going to give me 2 secant theta times tangent theta, and then I have 2 of these minus 4 of the same thing, so I have minus 2 ln absolute value secant theta plus tangent theta plus c. Okay? Now I just need to convert it back into our x universe. First thing I want you to notice is that u is equal to e to the x, and u is also equal to 2 secant theta. So I'm going to bring those 2 together with the transitive property, and notice that e to the x is equal to 2 secant theta. Right? Okay. On top of that, I have this relationship as well, that this square root is equal to 2 times tangent theta. And we know that u is equal to e to the x. So that means that the square root of e to the 2x minus 4 is equal to 2 tangent theta. So I'm bringing together both of my substitutions to reverse them simultaneously. And I'm now going to use these two facts to finish filling out this. So 2 secant theta is e to the x. And then just tangent theta by itself is going to be 1/2 of this. So all in all, it's going to be 1/2 e to the x times the square root of e to the 2x minus 4 minus, now 2 times the ln, I'm going to have to keep that as is, 2 ln absolute value, secant plus tangent. These two are going to have the same denominator of 2. Because notice, to do secant and tangent, I have to divide them each by 2. Okay? And it just ends up being the e to the x plus the square root of e to the 2x minus 4. And then, of course, plus c. So something that started out with a simple substitution, and then I also used a trig subs, I actually could have done them simultaneously even at the beginning, this same way right here. I just broke it apart to make it easier to follow. Okay? Let's finish up this lecture talking about one other structure that can be handled with trig substitution. It also has a few other options with one of the other methods we'll talk about in a later section. But this is something that you need to know can happen, and that you need to be ready to do in the event that it comes up. See here, I don't have a binomial anymore, but I do have the x squared, and it's a very simple quadratic form, right? Same thing with something like this. So what I can do, though, to make it work with trig substitution is I can complete the square on the quadratic portion in order to force it to be some sort of sum or difference of things that are squared. That's what completing the square does. So if you're rusty on your completing the square, then time to practice, time to buckle up. And if you really need to hit it hardcore, go to my college algebra series, and I have an entire lecture video just on completing the square close to the beginning of that series. Okay, so I'm going to complete the square here on this piece. I have x squared plus 10x plus 29. I'm going to put the plus 29 out of the way. What you do is you take half of the b term, so in this case that would be 5, and I'm going to factor that into x plus 5 squared. But if you FOIL out x plus 5 times x plus 5, notice you'll get x squared plus 10x plus 25. Okay, so then what I'm going to do right next to that is I'm going to put a minus 25 to balance that out. And notice that these front three terms factor exactly into this. And then I just need to simplify these two. So minus 25 plus 29 does give me a plus 4. All right. So what that means is if I complete the square on x squared plus 10x plus 29, it can be converted into x plus 5 quantity squared plus 4, which that happens to be a sum of squares. X plus 5 is squared, and 4 is 2 squared. So that sets me up exactly where I need to be. This integral would then become this, x over the square root of x plus 5 squared plus 4 dx. And now that this is a sum of squares, I can start using my trig substitution setup. So that's what we'll do now. I'll draw my triangle. Okay, in my triangle, I will start by noticing that it's a sum of squares. So I'm going to use the two legs. The bottom will be a 2, because that's 2 squared is 4. The other leg will be x plus 5, so that I have my two objects represented here. The hypotenuse will then be the square root of x plus 5 squared plus 4, right? Because it's this squared plus this squared, square rooted. Which is great, because that's exactly what I have in my integral there. Okay, so then opposite over adjacent would give me tangent. That means that x plus 5 is going to be equal to 2 tangent theta. Now x plus 5, the plus 5 doesn't change anything for the derivative. If I take the derivative of x plus 5, I still am going to get dx, right? Because the derivative of 5 is 0. So dx is still going to be 2 secant squared theta d theta. And then on top of that, I can notice that the hypotenuse divided by the adjacent would give me the radical that I'm interested in. The x plus 5 squared plus 4 is then equal to 2 times the secant of theta in that sense. All right. So I've got my trig substitution ready to go for this guy right here. Okay? To make this x work out for me, I'm going to have to do a little bit of solving here. Notice that x plus 5 is 2 tangent theta, so x is going to be equal to 2 tangent theta minus 5, right? I mean, it's the same thing. I just subtracted the 5 from both sides there. And that's what x is going to be here. So then I have an integral 2 tangent theta minus 5 over the square root portion is 2 secant theta, and dx is 2 secant squared theta d theta. Okay, so right away I can reduce these 2's, right? Those are gone. My secant theta here is going to take away one of these, so I'm just left with a secant theta. I'm going to take this secant theta and I'm going to distribute it into these parentheses here, so that what I've got is the integral of 2 secant theta tangent theta minus 5 secant theta, both of which are antiderivatives that I can easily kick out, right? Okay, so the antiderivative of secant times tangent is just secant, so I have 2 secant theta minus 5 times the ln, absolute value of secant theta plus tangent theta. And then, of course, don't forget your plus c there. Right? Okay, so let's finish up by getting back into my x universe here. 2 secant theta is equal to the radical here. So my final answer here is going to be the square root of x plus 5 squared plus 4, because that's what 2 secant theta is equal to, minus 5 times the ln with an absolute value. Secant theta is going to be the square root of the x plus 5 squared plus 4 over 2, right? Because I just divide by the 2 here. And tangent theta, right here, tangent theta is equal to x plus 5 over 2. So plus x plus 5 over 2 plus c. To make the answer a little bit simpler, sometimes what people will do is this. They'll notice that these two have a common denominator of 2 here, and make it just one big fraction over 2, like so. So a particularly interesting one. Also, another alternative here is, instead of writing the radical with the completed square here, remember that completed square is actually equal to this original polynomial here. So I could just write square root of x squared plus 10x plus 29 for this portion here. That would also work. Right? Let's go one more time. I'm going to have to complete the square on this one because, again, 8x minus x squared is not a sum or difference of squares because of the x. If it was just 8 minus x squared, I could probably get away with it. Just I'd have to deal with the square root of 8 instead of something nice and pretty that's squareable or easily square rooted. But because of the x, I can't do that. All right? It's a quadratic, and I need to complete the square on it. So that's what I'm going to do now. I take the 8x minus x squared, and I'm going to write it as negative x squared plus 8x. To complete the square, you always want x squared to have a simple 1 coefficient. So I'm going to start by factoring out the negative, which is going to give me this. Notice I left a little blank there. To complete the square, remember you want to take half of that middle number. So I'm going to have x minus 4 squared. Okay? Now in your mind, multiply out the x minus 4 squared. That's going to be x squared minus 8x plus 16. Like this. But what I've done is I've technically created a negative 16. So to balance that out, I have to put another plus 16 out here, which at the very end, this plus 16 would have to follow here. Okay, now because of the way this subtraction is written, I'm going to reverse this around to look like this. And this is the completed square version of that original quadratic. Okay, recap. Why are both of these plus? Because I put one of them inside of a parentheses with the negative hanging out here. So technically that's a negative 16 balanced out with a positive 16. Notice it has given me a difference of two things that are squared. So my integral then becomes integral 1 over 16 minus x minus 4 squared dx. Okay, since it's a difference of squares, I can then proceed into trigonometric substitution. I'm going to draw my triangle. I notice that it's a subtraction and 16's in the front, so I put a 4 hypotenuse. And then for the other leg over here, I'm going to put x minus 4 so that I can get my sign set up. And then that makes this bottom leg a square root of 16 minus x minus 4 squared, which is what I've got here. Just, not the square root in the integral. Okay, so let's continue setting up the substitution. That means that x minus 4 is equal to 4 sine theta. Right, because opposite over hypotenuse is sine. The derivative here, dx, is then equal to 4 cosine theta d theta. And adjacent over hypotenuse, I can say that the square root of 16 minus x minus 4 squared is equal to 4 cosine theta. So I don't have everything I need. I have almost everything I need. I have the dx. I don't have any free-floating x's. What I do have is this binomial right here, though, the 16 minus x minus 4 squared. But I don't have the radical in the integral. So what I'm going to do is I'm going to continue this one step further by squaring both sides. So just 16 minus x minus 4 squared, like so, would be equal to 16 times cosine squared theta. Right? That's directly from here to here, separate from the x dx pair. All right, now I have the pieces I need to do this substitution. I have my integral. 1 is still on top. the 16 minus x minus 4 squared is equal to 16 times cosine squared theta. Dx is equal to 4 cosine theta d theta. I can then reduce this integral by doing 4 over 16, which would give me 1/4. And cosine would wipe out one of these cosines, leaving me with the integral of 1 over cosine theta d theta. But of course, 1 over cosine theta is really just secant theta d theta, which again, we've been using that antiderivative a lot, right? That one seems to come up a good bit. The antiderivative of the secant is going to give me 1/4 ln absolute value secant theta plus tangent theta plus c. And then I just need to bring that back into my x universe. So I need to figure out what secant theta and what tangent theta are. Those are not listed in my original substitutions over here. So I'm going to go back to the triangle to figure that out. Secant theta is the hypotenuse over the adjacent. Okay? So I've got 1/4 ln absolute value of 4 over square root of 16 minus x minus 4 squared plus tangent theta is opposite over adjacent. So that's going to be x minus 4 over the square root of 16 minus x minus 4 squared. Now notice both of these have the same denominator again. And if I do 4 plus x minus 4, that works out really nice. It gives me just x. So I can finish this up with a 1/4 ln absolute value of x over the square root of 16 minus x minus 4 squared. And again, just like in the last one, you could actually rewrite the 16 minus x minus 4 squared as, 8x minus x squared. They're equivalent, right? That's what completing the square was all about. But it's also fine to leave it like that. So I hope that this lecture has expanded your mind as to what we can do with substitutions. And it's not just about replacing chunks with variables. It can also be about completely changing the structure into something that has a different flow and sometimes an easier path to see to the end of these.